Welcome to LACAR 21. My name is Jose Carlos, and I am going to present robust angular velocity control of a VTOL-UAV for aggressive maneuvers flight. This work presents the design of an autopilot for acrobatic maneuvers, such as multiple flips, invert itself completely, and backflips. This flight mode is possible by controlling the angular velocity of the UAV instead of the attitude. A robust angular velocity control is an approach that allows to follow aggressive reference at high speed to generate acrobatic flights. The algorithm uses the active disturbance rejection control to estimate and eliminate effects that are generated in these type of flights, such as unpredictable dynamics, external disturbances, and ground effect. The control algorithm is parameterized by quaternion, avoiding the gimbal lock, singularities. In addition, the maximum torques of the rotor are taken account by means of a saturation function. In recent years, the development of unmanned aerial vehicles for vertical takeoff and landing have received notable growth. The quadcopter is the standard platform for the development of control system, trajectory generation 2, cooperative control, aerial manipulation, and aggressive maneuvers. Undoubtedly, its high maneuverability, simple design, and reduced size are factors that favor its use in applications. Some examples of these applications are search and rescue, precision agriculture, aerial photography, disaster relief, among others. However, designing control algorithms for stabilization of their states is not trivial. Since the quadcopter is non-linear system, underactuated, perceptible, subject to external disturbances, and parametric uncertainties. This research addresses the problem of designing an autopilot for acrobatic maneuvers, such as multiple turns, inversion of the quadcopter completely, and invert somersaults. This flight mode is possible by controlling the angular velocity of the UAV instead of the Euler angles. Performing high-speed maneuvers will generate unwanted effects, such as high oscillation, transients, turbulence, and ground effects, which are difficult to model. For this reason, a control with active disturbance rejection is proposed, which means of an external state observer estimates the total disturbance on line. Once the total disturbance has been estimated, a bounded control based on quaternions is used together with the action of the observer to close the control loop. The algorithm is relatively simple to implement in embedded systems with limited processing power. Okay, here in the mathematical model of a quadrotor or quadcopter, the quadcopter consists of a rigid transverse frame that contains 4 rotors at its ends. To derive the equations that describe the attitude and position of the VTOL, it is necessary to consider 2 orthogonal coordinate frames. The first is located at the center of the mass of the quadcopter, and the inertial coordinate frame, the second, is located at some point in the Earth's surface. The parametrization by quaternions are used to describe the attitude allowing nonlinear large angles, aerobatic and high-speed aggressive maneuvers. For introducing the quaternion, we have the following equation, where Q sub b and Q sub 0 satisfy the following equation. The unit quaternion Q represents the rotation of the frame through the map. The mathematical model that describes the kinematic equation of rotation of the quadcopter is given by the following equation. Then, the quaternion that represents the attitude error between the current orientation and the desired one is given by the following equation. The attitude dynamics is mathematically described as the following equation. In that equation, we have the inertial matrix that it's described by J. Then we have G that seems the gyropic. Then C is the time dependent to external disturbance. And tau is the vector that contains the moments generated by the difference between the angular velocity of the four rotors. The main objective of this work or paper is to present the design of a robust control and be able to follow varying angular velocity in time. Also, the UAV VTOL is subject to external disturbances. Parametric uncertainties and unpredictable dynamics can be formalized mathematically as in this equation we have W sub t is the time dependent with the desired velocity. Q sub d is calculated from the kinematic equation, and zeta is the total disturbance. Okay. The control strategy takes into account the maximum torques allowed by the rotors. This can be formulated as where the tau represents the bounds of the control torque component. Okay. Now here comes the entire figure of the system. We have here the structure of the proposed control algorithm, and it is divided into three blocks. First of all, we have the attitude mode kinematic. We could see how the desired angular velocity is entered to attitude mode kinematic, and we obtain the quaternion with respect to time, and then both enter to the control, to the attitude ADRC controller. Then we have the state of the observer, and it contributes. The observer estimates the total disturbances, and it enters to bounded attitude control. Okay. For this purpose, one has the following assumptions: the total disturbance estimation, angular velocity estimation, and its time derivative will be denoted by the next characters, respectively. The perturbation function zeta is a uniformly, absolutely bounded disturbance. The desired velocity is uniformly, absolutely bounded first order time derivative. Okay. Then the attitude control is structured by three blocks. First, the error quaternion. Second, the bounded attitude control, and at least the observer. First, the disturbance observer will be defined grouping endogenous terms depend on the state, and the exogenous term depend on the time. Then we obtain the global perturbation of the system, and we could condense it all in the following equation. In this equation, we have again the inertia in the inertial matrix, the gyroscopic, and the perturbance. Now consider the following observer. Given a positive constant, a continuous known decreasing function is defined by, in the proposition 1, we consider the rigid body rotation dynamics, and it is described by the following equation, and bounded control input vector tau such as, where the saturation is defined by, and where the both saturation functions. Okay, first, in our first result, we have the evolution of the external disturbances in red color, and then in black we have the estimation. Then we have the observer, and it has been used with the following parameters. And then we obtain the next equation. Then we have a graphic that represents the trajectory tracking double flip. And we could see what happened with the quadcopter. Then we have some results, and we could see the evolution of UAV VTOL states. Okay, first, in the A graphic that is colored by blue, we could see the attitude evolution. A conversion is made to Euler's angles for easy interpretation. Then, in V, color red, we could see the evolution of an angular velocity, the angular velocity. Then in C, with color green, is the position evolution, and D is the linear velocity evolution. Then we obtain the following results and equation. Okay, in conclusion, we could say that the control law presented shows robustness to endogenous and exogenous shocks. Due to its simplicity, the control strategy can be implemented in computer systems with low computational power. The control is robust enough to follow trajectories to generate aggressive maneuvers with high precision. Okay, we have the reference, and thank you for your attention.